Chapter 12, Part A, Deflection of Beams and Shafts. Example 1. We already find that by having a curvature equation, when dy over dx goes 0, it changed to a 1 over rho is equal to d squared y over dx squared, and that's a equation of elastic curve. So by having the elastic curve equation, which is this equation, d squared by over dx squared is equal to a moment equation over ei, then we can easily get the calculation to extract the elastic curve. For example, in method 1, that's from the moment, which is if by if you integrate d squared by over dx squared, which is the equation of moment over ei. For the first time, it just gives you a ei dy over dx, which is the theta itself. And by the second integration of that, you can easily reach to delta equation. Mhm. And the second method is a determination of elastic curve directly from the load distribution. So if we know d squared by over dx squared is the equation of moment by a derivation of that, so a derivation of moment area under shear is moment, so derivation of a moment is giving us a shear, so that's a d to the power of third over of y over dx cube. Then by the other, if you integrate derivate it once more, you will reach to the w. So a derivation of moment gives you m, derivation of moment gives you m, derivation of moment gives you shear, and derivation of shear gives you a w, and the negative just the downward direction of float. So it says if you only are provided with the load function of w, and by 4 consecutive integration from load, you can reach to elastic curve equation, which is delta. Mhm. So let's put it into an example to see how that works. Again, we understand that's 1 over rho is equal to this nonlinear second order differential equation. By a simplification, we get to this equation. And then what if we have a cantilever beam handling a uniformly distributed load of W in terms of mass point of view, Wx by integration goes to a shear, or V, which is the area under load. Area under load goes by shear, and from the conceptual point of view, load, by integrating the load, we can get the shear. And by a second integration from the Wx, the first one get us to shear, and the second one, area under shear, is the moment. So from the conceptual part, also load goes to shear by integration goes to moment. And by the third integration, it says if you integrate the area under moment from 0 to L dx, it gives you the slope, and that's a load goes to shear, goes to moment, goes to angle of bending. And the fourth consecutive integration get us to a de delta, or deflection of beam, which is in area under a slope gives you delta. So from the conceptual part of view, load, area under load is shear, area under shear is moment, area under moment is angle of bending, area of uh, under angle of bending is gives you maximum deflection. So that's theta and delta. Mhm. So for example, in these two cases, if we have a these, if you compare beam one with beam two, the first one, which is a two simple support handling a uniformly distributed load of W, has a delta maximum of 5 WL to the fourth over 384 EI. While if you just have the same beam with the same loading, but if the two ends go by fixed support, it just the numeric value of delta maximum goes far below that number. So it goes to what by 1/5. So how that goes? So if you make a comparison between these two beams, you can easily see the top one goes by 5 degree higher or five times higher than the below, just because of the support. This is a two simply support beam, and this is fixed support. So that goes by delta max goes by W L to the 4 over 384 EI, and this one goes by 5 WL over 384 EI. And that's only due to the, the difference in their supports. This is a sample of a two-end fixed beam in Abacus, and that just gives you the mesh and also maximum deflection with stress distribution. In Let's go to our example. Example, it just says a two-end simple support beam handling a uniformly distributed load of W. So a part of it, it's one half is L over 2, so the other L over 2, so the total length is L. So we want to have equation of elastic curve and also delta max. So let's see how to attempt this problem. So we solve it in two approach. The first one is the determination of elastic curve from the moment equation. So by uh, developing the summation of forces in y direction goes zero, that says both supports should cancel out WL. So a sigma MA goes zero gives us RB a half of WL, and due to symmetry we do know they should be equal to each other, so RA is equal to RB, and each of them goes by a half of WL. Now this time by replacing the numeric value of RA, but this times go by the length of X and develop the moment about X, and that's convert the distributed load to a concentrated load of Wx by the distance of x over 2. And if you just develop the moment of sigma m x equal to 0, it just gives you the equation of moment. So by rearranging that, it just gives you mx is equal to a positive of wl x over 2 minus a 1 over 2 wx squared. Mhm. Then if you remember, we told m over ei is d squared y over dx squared. If you just take ei over this equation, it just gives you the equation of moment. By integrating this equation, it just gives you ei times dy over dx, which is the theta. And by the second equation of moment, the second integration of moment, it gets you to eiy, which is the delta, which we are looking for. We are looking for delta max. So what then? Then mx is equal to this equation. Integrated once gives us the theta, and by each integration, an integration constant develops. So if we call this equation 1 and integrate it once more, it just gets us to the delta or deflection of beam. And again, by each term of integration, a new constant uh, arrives. So that's if we call this equation 1 and 2, and we do have two integration constant of C1 and C2. And by each constant of integration, we need a boundary condition. So we have two of them, we need two boundary conditions to solve our problem. So at x equal to 0, y is equal to 0, if we call that a, and at x equal to L, again, y is equal to 0 because they are at our supports. We cannot move any distance or upper or lower than the point A or B. So having these two constant and these two condition, we can get the constant easily. So if we have equation 2, a and b, a and 2 gives us c2 is equal to 0 and b and 2. So this is b and 2. It just gives us c1 is a negative 1 over 24 wl cubed. Mhm. If you replace c1 and c2 in the main equation at the top, so it just gives us ei times y is goes by this equation. And if you rearrange the equation, it just says y or delta is equal to w over 24 ei times 2 lx cubed minus x4 x to the power of 4 minus l cubed times x close parenthesis. So how that goes, if we know delta maximum due to symmetry occurs or happens at the center, so that's x is equal to L over 2 by this equation, and then y max goes by a again, uh, this is the number we already talk about, but we just do the mass calculation for 5. A negative is just the direction, 5 wl to the fourth over 384 ei. So that's delta max. If we want to calculate the delta, we just need to come back to equation 1. So by replacing the equation 1, dy over dx is theta. Mhm. And if you solve it for x equal to 0, it just gives you and x equal to L because they are identical to each other due to symmetry. It says theta is equal to theta A is equal to theta B is WL cubed over 24 EI. One can say delta maximum of a two simple support beam happen to handle a uniformly distributed load of W. Delta max is 5 WL to the power of 4 over 384 EI, and theta A is identical to theta B, and it's equal to WL cubed over 24 EI. That's the deflection behavior of beam, and thank you.